Hello and welcome to the next video in this series as we learn Prolog together. Today we're going to practice recursion in a different way, which will give us the opportunity to learn about lists a little more. We've already come across them, but learn a little bit more about lists and also practice deriving a recursive definition. So what we're going to be doing is we're going to be asking a very simple question, and the question is, are two lists the same? So if we say, here's a list, apple, banana, orange. That's the first list, and we've got another list, apple, banana, grapes. Now, just as a refresher, if we have of some properties of lists, we've already done this, but just as a refresher, if we have a list A, B, C, that's not the same as A, B, C, because repetition matters, so that's not the same, and order matters as well, so that's not the same as A, C, B. So yes, they contain the same elements, but the order is different, so that's kind of worth just refreshing our memory. So we're asking, are these two lists the same? And let's just, like a good way to solve many of these kinds of Prolog problems is to think through in plain English how you would do it with pen and paper or pencil and paper. Well, if I was given these two lists and asked the question, are they the same? I might say, well, the first element matches, the second element matches, and the third one doesn't, so they're not the same. And if the third element was orange, then they would match and be the same. And by working through that kind of almost obvious statement, almost obvious thinking, I've almost kind of seen the mechanism at play. And the mechanism of deciding whether two lists are the same is to see if we can match the elements. So one way of saying if two lists are the same is to work through and match every item. So if we try and write a Prolog property, and we say X, Y, Z, that's one of the lists, and another list is A, B, C. These are variables, so they'll match with whatever we provide. That's the same. How is this true? This is true if X equals A, Y equals B, and Z equals C. That's what we've just done here. And you say, okay, that makes sense. By the way, just as a reminder, this equals is not assignment. So almost all programming languages say X equals 3 plus Y, that would be the value of this would end up in here, so it's an assignment. In Prolog, that's not what equals does. In Prolog, X equals is unification, and we've talked about unification earlier. Go back to that video if you need to, or look at the blog, but it's about matching two things to see if they can become the same. So that's worth just reminding yourselves what unification was. So it's almost equivalent here, but that distinction is important. So we're saying, can X and A be unified? Well, if X is apple and A is apple, then they can. The same here, Y and B, banana and banana, they can be unified. And Z and C, orange and grapes, can't be unified. They don't match. So that one would fail in this example, and therefore same would not be true. And this is fine as a definition for lists of length 3. What about lists of length 2? Well, actually that's simpler, isn't it? That's same X, Y, and A, B, and that's true if X equals A and Y equals B dot. What about a list or lists of length 5 or 10 or 100? Then you can start to see the problem with this approach. If we are interested in a definition of same that works for lists of length 3, 4, 10, 21, 31, we don't want to write lots of these kinds of definitions. One, it's impractical, it's inelegant, and there may actually not be enough rules that we've written to catch that one case. So if we wanted to write, if we wrote 100 of these and then actually the query was with a list of length 110, that wouldn't have been sufficient. So we clearly need a better way. So let's draw a picture of another way we might solve this. So let's imagine we've got two lists of arbitrary length, although there might be 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. So these are of length 8, but let's forget that they're 8. There might be 10 or 12 or something else. Is there a better way? And because we're in the theme of recursion, you can imagine the answer is recursive. So two lists are the same if the head, so this is list 1 and list 2, two lists are the same list 1 and list 2, I'm just thinking loud here, are the same if the heads of the list are the same. So let's imagine there's a magic way of pulling out the head, head of list 1. This isn't Prolog, this is just me writing what I'm saying. If the head of list 1 equals the head of list 2, if the heads are the same, and, remember the comma means and, the tails, tail, head, so the head is just the top part, like that, and the tail is the rest. And if the tails are the same, so that's T1 and T2. Again, this isn't proper Prolog, this is just me thinking aloud. Let's say that again. Two lists are the same if the heads are the same and the tails are the same. That sounds obvious. It sounds so obvious that it sounds like it shouldn't be useful, because we are defining same in terms of same, and that feels like it shouldn't help us. It feels like a tautology. But remember that crucial point. This has reduced the size of the problem. The tails are one size smaller because we've chopped off the head of the full list. So this question is about the full list, this one here, and this question is about a smaller list reduced by 1. These lists reduced by 1. So it looks like it could be useful. So two lists are the same if the heads are the same and the tails are the same. And then we go into that recursive cycle of asking, well, how are the tails the same? T1, T2. They become the new list that we want to test. And those are true if the heads of these things, that one and that one, is the same. So the heads of T1, T2 is the same, and the tails are the same. So these tails are the same. And to do that, answer that question, we then compare. You can see what's happening here. If the heads are the same and the tails are the same, and so on, until we get to almost the end. So let's see what would happen at almost the end. So we started off with long lists, and now we end up with two short lists of size 1, 2, 3, 4. So size 2. So these are the same if the heads are the same and the tails are the same. So that will then turn into a question about the tails. Now the tail of a list of if this is size 2, then the tail is a list of size 1. So imagine we've got, let me write that out properly. If I have a list of size just 2, let's say A and B, the head is A, and so that's the head, and the tail is the remainder, which is a list there, which happens to have one element in. This is important what we're saying here. The head is always an element and the tail is always a list. See, the head is always an element and the tail is always a list. So the head is A and the tail is a list, which just happens to have one thing in it. And then when we apply this rule again, we're asking what is the head and tail of this thing here. So the head of this is the first element. So the head is B, and the tail must always be a list, but it's empty. So that gives us a clue as to what the stopping rule should be. So the continuation rule is this one. This one is the continuation rule, and the stopping rule has to be, stopping rule is 2 lists are the same if they're both empty. That's just true. So we'll eventually end up at the empty, comparing empty lists. So before we go back to code, I'll just kind of illustrate that one more time. We're saying that 2 lists are the same, 2 lists L1, L2, if the heads are the same, H1, H2, there you go, H1 and H2, H1, H2 are the same, and the tails T1, T2 are the same, so that's T1, T2. So that chops off the head, compares them, and then asks are the tails the same, and we keep applying this rule until we keep chopping off the heads, comparing them, until we end up with 2 lists that are empty. So we need a stopping rule that says 2 empty lists are just the same. There's no condition. The condition is empty. So that's just true. So we will eventually end up with 2 empty lists if we keep chopping off the heads. So that's the stopping rule, and that's the continuation rule. You might be asking, what if 2 lists are not the same length? Like this. So if we chop off the heads, compare those, compare those, compare those, and that one will run out, and that one won't have run out. And if we don't have a rule that matches this scenario, it's false anyway, so it fails, which is what we want it to do. We'll talk through that again with an example in a minute, but let's go back to a simple kind of code to bring it to life. So here, very small example, isn't it? So this is a really interesting thing. I've said it before, and it's worth saying again. With recursive rules, they are often very small and elegant, but they kind of hide the fact that a huge amount of thinking had to go into them, like we've just done. And here's the rules, the 2 rules, the continuation and the stopping rule, to see if 2 lists are the same. Let's write that out. Same is defined in terms of same, and the stopping rule simply says that 2 empty lists are the same. You might be thinking, well, what's all this? This is new. Let's write that out. So here we want to have our 2 lists that we're comparing, this one and this one and this one. What's this? This is new. Well, what this does, it's a way of chopping the head off a list. It's a way of decomposing a list into its head and tail. So if we've got a list, L1, and we unify it with H and T, just a list L, what H becomes is the head of that list, and T becomes the tail of that list. So that's H, and this is T. So this is how in code we take a list L and we can separate out the head from the tail by unifying this structure, and there's a vertical line here, that vertical line there. So that's just a standard format for chopping off the head of a list. And it's not really chopping it off. What we're doing here is unification. Again, it's the equal sign. So let's just look at some kind of examples. So if my list is 3, 4, 5, if I unify that with HT, so this outer bracket, square brackets, tell Prolog that we are comparing, lists, that's a list and that's a list, and then H becomes 3, and the tail is, so H becomes 3 and tail becomes a list, which is 4 and 5. Let's just look at some other examples of that kind of unification. So that's just a visual picture showing a list, A, B, C, D, E, F, and when we unify that list with a structure of 2 variables with a vertical line between, that becomes a head and that becomes a tail. So H is A and T is this, and H is always the element and T is always a list, the remainder list. And on the blog you can see some examples. So if we have a list of 1, 2, 3 and unify it with H, T in that way, the head is 1 and the tail is the list 2, 3 there. If it's a longer list, then the head is still the same, but the tail is longer, 2, 3, 4. If it's 1, 2, a short list, then the head is 1, which is the first element, and tail is still a list, even though it's one item, it's still a list. So it's a list of one item, tail is always a list. That's a golden rule there. If it's empty, then unification fails. Now that's not bad, that's actually good, because we can write our rules, we can write Prolog knowing that when we reach kind of chopping off, working through a list and reach an empty list, then it fails, and that's we can use that. You'll see how that works. We won't go into it now, but in future you might come across lists which contain lists. So here is a list of 3 elements, that one, and that one. And the first one is actually a list itself. So the head becomes the first element, which is a list, which happens to contain 1. So whatever the first one is, whatever object that is, H becomes that, the head, and the tail is the remainder. And here's a more complicated example of a list of 3 items. The first item is this list, second item is that list, third item is that list. So the head becomes this first item element, which is a list, ABC, and the tail is a list, the remainder there. So that's just for what you might see in future. So let's just practice that unification with lists. So if I've got a list, let's say A, B, C, D, and if I unify that with that structure we talked about, what we're asking Prolog is, how can this be true? It can be true when H unifies with A and T unifies with a tail. There you go. And if we shorten that, we should get the head is A and the tail is again always a list B. And we want to try the empty case, which should fail, and that's false. Great, so we've tested that. Now let's test our definitions same to see if it works. So ABC is that the same as another list A, B, C? Let's run that, and it's true. If I change one of them so they're not the same, then it's false. So we've talked through in plain English the method, the algorithm. We've seen it working. What I'm going to do now is just talk through in detail what Prolog is doing here, just with that example. Again, the point of this is to see the mechanisms at play, even if every day we don't always think in that level of detail. So let's do that. Right, so here are the Prolog program. If there's no facts, actually, it's just, well, it is a fact. This is a simple fact, and this is the relation. It's worth saying, actually, at this point, that a fact is actually a full rule with an empty body. So we know we said we had a head and a body for a rule. A fact like red apple, that's actually the same as saying red apple is true if, and then having an empty body, so it's always true. So what we're saying now is that facts are rules with empty bodies. So just something that we didn't say earlier because we don't want to confuse you too much, but we can say it now because we understand it a little bit better. So facts are actually rules with empty bodies, but that doesn't change how we think about them. So this is the definition, that's the stopping rule, and this is a continuation rule. And we are going to try and work with a question that we're asking, which is same A, B, C. Is that the same as A, B, C? That's the question. And we're just going to work through the detail. So Prolog will look at this and say, this is about the property same. Is there something in the database about property? Yep, there's two rules, same and same. Let's apply the first one, and that has empty list and empty list, and that doesn't unify because this is not empty and that's not empty, so that one fails. So let's try the second rule, this one, and this is saying that same H1 tail 1 H2 tail 2 is true if H1 is the same as H2 or unifies, and then the tails are the same, T1 T2. Now how does that unify? Well, H1 becomes A and T1 becomes BC, H2 becomes A and T2 becomes BC. So that is asking if A equals A, that's true, and this is then asking same if B comma C is true, and B comma C is the same as B comma C. That's then that needs to be satisfied. Notice again what we said earlier with recursive definitions, the going through the cycle of applying the definition reduces the size of the problem. So this problem is about lists of length 3, and now we've reduced it to a question about lists of length 2. So A equals A, and now we have a new query goal that we need to satisfy. So let's do that one. So same BC, that's the question, and to satisfy that, that's only true if, well, what will Prolog do? It'll first try this rule, and that fails because these are not empty. Let's try the second one, and then that becomes, through this unification, testing if B equals B, and same the tails, which are C and C. So now we've reduced the question to lists of length 1. So 3, 2 and 1. Can you see how it goes down the ladder, as it were? So B is true. So now we've got the next step, so same C, that's true if the heads are the same, because they, well, let's step by step. So the first rule again fails because these are not empty lists. So this second rule we try again, and here the heads are C, H1 becomes C and H2 becomes C, so we're testing if C equals C, that's here, and same with if that's true of the tails, and the tails are now empty, so that's true. And is this true? Same, empty list, and now that does match the stopping rule. Same, empty list is just true, so this is just true. So we found the stopping rule now. Phew, that was a lot of work, but you can see how that it's worth kind of going through that once. What would happen if the second list had it was longer, had a D in it? So this would eventually work its way down to C comma D, and let's try a different color there. C comma D. So C would be the same, the heads would be the same, but then the next question would be trying to match, to say, are these two lists the same, empty and D? Now that doesn't, this question doesn't match the first rule, because this is empty but this isn't, so we have to apply the second one. And what happens here is same, empty comma D, the deconstruction of this with HT, head and tail, that fails, and because that fails, the rule fails, and therefore, which is good for us because that fails, and the Prolog will then say, yep, the original query has failed. ABC is not the same as ABCD. That's failed. No other rule will match that. So that's kind of, that works. Just wanted to show you how that works. Again, look at the blog if you want to kind of see that written out in more detail, in neater words as well. If you look at the blog, there's worked examples. The one we've just done with 1, 2, 3 there, the first example. The second one is with unequal lists, and it just talks through how that works. So 1, 2, 3 is not the same as 1, 2, 4, because eventually the heads, so 1 and 1 is the same, 2 and 2 is the same, but 3 and 4 are not the same. So when you apply those rules, you'll eventually compare 3 with 4, and that would fail. Lists of different length, we've just talked about that. We used A, B, C, D. In the example is 1, 2, 3, 4, and that last one won't unify because the empty list doesn't unify with that construct. And what we can do is use variables as well. So if we put a variable in the query, we're asking how can this be true? So this can be true if x is a. So let's run that. X is a. If we say put a D there, or let's put elephant, just to be really wild. How can this be true? In looking at it, you know it can't ever be true. No value of x will ever make these two lists equal, because C is not the same as elephant, so that will always fail. So that's useful. And we can ask a broader question. We can say which list x makes x the same as ABC list, and the answer is ABC. So that's just, it's useful with Prolog definitions to first work through them with specific examples, grounded examples, and then later try them with variables, because it allows us to ask different kinds of questions. Just as a teaser for what we might cover much later in the course, I won't run this asking which x and y are the same lists. If you think about it, there's an infinite number, so Prolog will run into some problems. But that's just a teaser for the kinds of things we will look at later. Fantastic. So I think I'll stop there.